Again, write down as well, but I'll stop here so we know better.
Man, that's interesting. An interesting history. So we actually have a second speaker here from Google, and I'm going to butcher your name right now, but Yaroslav Bulatov.
Yes.
Bulatov?
Correct.
Okay. All right, close. Yeah. All right. And let's probably just pull this out here. And do you want the little clicker thing for the slides?
I'm not sure it's very to me.
Just
Does it just simulate
keyboard presses or whatever. Can you give the little clicker? Oh.
I think so.
All right.
Some of the types behind
Somebody responded. So right there.
Yeah, actually I don't know.
Yeah.
Okay, thank you, Dr. Nack, for this wonderful history overview. And I will talk about, speaking of the hype, I will talk about an actual application where Google came in and we had a problem where we had to use humans to do it, and we came in and we replaced them with human networks. And we freed up those humans to do other more interesting tasks. This task, the solution is described in this paper. So this is a submission we did to ICLR. ICLR is the International Conference for Learning Representations, and it's, I think it's a very good neural network conference. It started last year, organized by Jan Mikun. So it evolved from this conference called the Snowbird Workshop, but basically it's just this conference where you see some very good people with, it's like very focused on neural networks. And there's something special about this conference, it's their reviewing system. So normally you send a paper in and it takes some time to get reviewed and it's accepted or rejected. Here you send it in and it becomes visible immediately. So our paper has not been accepted yet. We send it in, but because of the funny way this thing works, we send it in, and then next day it got picked up by MIT Technology Review. And then the next 2 days it got picked up by Slate, Vice, Wired, and 10 other popular outlets. So it will be kind of funny if it gets rejected, because all those journals wrote about a paper which does not exist. So, what is the problem we had? So, we're building Google Maps and we need to know where addresses are. So this is a street view image of this house. So there's a 28. And the problem is you need to find the 28 and you need to read it. You need to know there's a 28 somewhere. So I'm on the optical character recognition team at Google. And our previous task was on Google Books. So we had to come in and then basically do OCR on Google Books and get it into Google Index. So we developed technology which is, well, open sourced it and improved it, and that's the technology that's used for indexing Google Books. And then our whole team, once we got done with that, our whole team picked up and we came to Street View to solve that problem. However, the problem is, once we took our engine that we developed for books and we tried it on photographs like this, it just didn't work. Just completely bad performance. And to see why it's bad performance, you can look how the traditional OCR works. So normally there's 4 stages. So first you have to detect where the text is. Then you kind of narrow your search to this line of text. And then you don't know where individual characters start, so you have some heuristics to suggest where they might be. So you produce some over-segmentation. So here you may have a single character split into 2 because you don't know if it's 1 character or 2 characters. Then you actually look at individual fragments, and then you try to see what they are. So an example, this is a 2 on the right one, it's a 2 from there. And you can see in the context, it's obviously a 2 here, it's not very clear. So it's actually a kind of you're losing some context here. And once you classified all the fragments, you do this Viterbi search, which is the same as in speech, so Dr. Nag knows a lot about that. So you try to infer the most likely possible segmentation of the text. This is an example of numbers we have to deal with. You can see why the original system may work badly. First, some of them are at an angle. How do you determine what angle it is? Some of them are using strange fonts like this one. There's some country in Europe, I haven't figured out why, which one, but it uses this as a 1. And you can see it can be difficult here. The digits, they're kind of merged into the fence. So it's a hard problem. So when I first, when we're given this problem, and I'm like, let's do it, my coworker said, well, and I wanted to use neural networks because it was becoming the next big thing. My coworker said, well, there's this 4 stages, just pick one of them and put neural networks in there. That'll be great. And then, you put the neural networks in one of the stages, you still have to connect them, tweak them, and it seemed like a lot of work. And I said, well, why not just do this? I have an image, and I put the whole image into the neural network, and my neural network just spits out the whole number. Or just told me, that's crazy, that's never going to work. And I said, well, I want to try it anyway. And the bottom line, the technical details are in the paper, but the bottom line is it worked, and now everybody in our team is all about neural networks. So this is a brief overview of the thing we used. So this AlexNet convolutional tower, that company that Google bought, Jeffrey Hinton, Alex Krzyzewski, they had this architecture that they used to win ImageNet. So I just used the same architecture. So we have this neural network, and then we have some fully connected layers, and then at the top I have several layers, one for each digit, and then just to read off the digit from their layers. And there are 2 architectures we use. So the one on the right we used for house numbers, and the one on the left we used for the paper for the publicly available data set. And the one with less parameters but with more hidden layers actually worked better. So I think it will also work better when we use it in production. I just didn't get to it yet. And this is just an example of the things it works on. So a normal approach where you start with finding the lines, correcting the orientations. This is an example of a thing that we'll have a problem with. But here it automatically figured out how to read those all the layouts. Okay, so that's all I have. Any questions?
So, what's the magic?
It's magic. Trust me.
Based on something like, like the random forest, or is it based on
Neural networks. It's based on
what
neural
neural
networks.
network?
This neural network. Convolutional neural network.
Okay.
Was it based on a scale-out architecture?
Which one?
To what extent is it a scale-out? Is it a scale-out architecture?
I don't know what it is.
Does it use a cluster of machines, or do you run it on the same machine?
No, I run it. Well, when we train it, we parallelize. So we do the thing that's called data parallelism. So we have many machines computing gradients on many data, and then we have a central server that aggregates them. And if you search for Jeff Dean neural networks, you'll find a paper which describes the architecture.
This is for a distributed optimization.
Right. So there's 2 kinds of parallelism we do. One, if you have a model which doesn't fit into a single machine, which is a pretty big model because we have 20 or 30 gigabyte RAM per machine, then you have different machines compute different parts of the model. But this model is not that big. So for there, we use a different kind of parallelism where you have a whole model in each machine, and then they're just computing, looking at different parts of data, and we have a central thing called parameter server that aggregates them. So basically, if you have 50 machines, you go through the data 50 times faster. And we're not using GPUs, we're using CPUs. Whenever somebody asks for a GPU, the answer they get, well, what if I give you 1,000 servers instead? But there are some people experimenting.
All right, so between you and me and everybody in this room, are you guys using CPUs because you guys have that available capacity, or are you guys not using GPUs because you guys do think that CPUs are actually a better choice?
We are using GPUs. I mean, I'm personally not using them because I got good results with CPUs, but there are people in other groups which use GPUs. And I think at some point I may hit harder tasks where I may benefit with GPUs, but right now, if I use 100 machines, it gives me good enough results.
How long did you have to train for?
This one,
100
so you get good results in a couple of hours, but then the remaining 1%, it can take a week.
Right.
So you train for a week.
Yeah.
Yeah.
What kind of? You said that Google doesn't yet have this in production because they've already got a lot of.
They do have it in production.
They do have it.
Yes.
Okay.
We have the one on the right.
Okay.
What does the output layer look like, the prediction? Was it really like, I heard somewhere that it was like 10,000
Okay.
separate numbers and then...
Right, so that's a very good question. If you want to predict the whole number, 243, how do you encode it? Right. So one way you could encode, you want to predict number from 0 to 10,000, you have 10,000 units. And then you say you activate each one of them separately. An alternative way to encode it, you have 50 units. So the first 10 units say what's the first digit, the second 10 units say what's the second digit, third 10 units say what's the third digit. Right. So that's the architecture I used.
I see.
So it's kind of factor architecture.
What was the learning algorithm that you used?
Gradient descent.
Just backpropagation?
Yes, backpropagation. Backpropagation on multiple machines. So basically you have multiple machines backpropagating and you have a central thing that averages them together.
What kind of accuracy rates do you get?
Accuracy, oh yeah, I didn't put that. So the accuracy, if we discard the 10% of the most unsure examples, it's human accuracy.
That's not good. Is that very good?
It's not very good?
Why is human accuracy?
Yeah, I mean, I actually did, so this is an example, I trained, I collected a data set of just single digits, 7 million single digit examples, and I just trained a big neural network on this much simpler task, and we got superhuman accuracy, meaning that the human makes a typing mistake more often than neural networks makes a prediction mistake.
How does it compare to like the zip code problem, or those are handwriting, of course, or the check? There are other systems for those separate domains. I don't know. Are there accuracy numbers for those, and how do they compare?
Yeah, actually I don't know how they compare. I think, so Jan LeCun did the implementation of neural network to read some number on the chart.
Those are single digits, though. You're doing
right.
Sequences of digits where they can
so maybe their accuracy is also
that's more
very
like
good.
Your problem's closer to the zip code problem, or the check rather than single.
Right, so I think their accuracy is also very good, but here the main contribution is that their approach, they have to do a lot of work. They have to come up with heuristics to over-segment. They have to implement vector search. And here we're just feeding in raw pixels as input and outputting things as raw output. So it's a lot less work. So that's the main contribution.
So, sorry, you zoom in, or you focus on one area of the picture to some degree, I suppose, to avoid having numerous addresses in the picture.
Correct. Yes, so I missed that, I didn't mention that part, but we actually have some EdaBoost-based detector that we run. So it's actually, this is an example of a patch that our system gets. So it's actually doesn't need to do complete text detection, but it needs to do a little bit of text localization.
And how much data was it?
100 million examples. Yeah.
How much worse would the four-step process have been compared to this?
The four-step.
You just use tesseracted.
Yeah, the tesseracted was as good as random. I mean, well,
Random.
maybe. I mean, it's a lot worse, like 10 times worse or 10 times worse. I mean, it was so bad we were like, okay, we need to do something else. Yeah. Yeah.
Is the algorithm fully supervised or is it semi-supervised?
It's fully supervised regular backpropagation. Yeah.
Did you try alternative architectures or did you go straight to AlexNet?
We tried a little bit of tweaking, but what we found is basically the bigger you make it, the better.
In terms of depth?
In terms of number of parameters.
Okay.
So more depth also helps a little bit, but what we found that things like learning rate and all the hyperparameters, if you make a network really big, then and train it for long enough, they all converge to the same accuracy. So basically, what we do is we try to make it as big as possible so it fits in memory, and that's what we train on.
So you just try to optimize like the depth versus width trade-off, like just that gets you to the
A little bit basic, but we usually just start with the biggest network we come in and train that.
Okay.
And then try to tweak things to improve it, but it usually doesn't help much.
Okay, cool.
How big was your training set?
100 million.
Oh, that's a training
Mm-hmm.
You mentioned on the two sides that the deeper network with less parameters was better.
Yes.
But you just said that more parameters would generally be better. Why do you think it was better?
I guess depth kind of helps. There was some other paper in ICLR which showed that depth helps. So maybe next time we'll start with that network. The thing is, when it takes a week to train, it doesn't. You cannot experiment much. So you kind of have a
GPU. You need GPUs.
Suddenly those 10,000 servers aren't looking so good, huh?
GPUs, or my theory is that we need a different way of training.
Yeah.
So right now, I think the problem is how do you parallelize, do data parallelism? You compute gradients and you average them together. So if you have a million machines, you average million gradients together, but a lot of them are bad gradients, so you kind of limited how good it does. So I think you need to do something smart, like taking the best gradient. But that's not been, that's experiment I'm trying, but I haven't finished it yet.
In production, how often does this get retrained?
Never. We train it and it goes. I mean, we just need to show that it's better than the humans, and then we definitely need the humans.
Where do you see the biggest improvements coming from? What things that...
Yeah, I think the biggest thing here is figuring out how to parallelize better. Because, as I was saying earlier, if you look at human brain, the information travels very slowly there. So actually, if we look at cloud, we have some cluster in Atlanta and some in Oregon, we can actually send packet there and back faster than the signal goes from one ear to another. So I think the biggest thing that's not solved right now is figuring out how to take the job of training a neural network, which is sequential right now. You have a step, and then you have another step, and another step, and figuring out how to have a different training procedure which is able to parallelize this. Yeah.
So while you're training, if one of your machines fail, do you just lose like part of your training set, or does the algorithm hold?
Yes, so basically in Google, you always have some machine fail, and some machines get hit by cosmic rays, and some machines are bad and they deterministically give you a wrong result each time. So basically, it's stochastic gradient descent, so it's already very noisy. You have some examples which have incorrect labels, so if you have a machine that gives an incorrect result or just dies, it doesn't really affect stochastic gradient much.
How much does the encoding of the inputs affect your performance? I guess you're using grayscale, or?
Yeah, so I experimented with color, and I found that color was 3 times slower to read, but didn't give any improvement. So I just used grayscale and just fed raw input, raw pixels.